Hi, welcome to Statics and Dynamics. Today we are going to look at a very high level view of what it takes to do analysis for structural safety. We saw the example with the chandelier where we did some free body diagram, calculated all of this. Usually it looks like an ad hoc series of steps, but I want to show you that there are 5 steps. Each step is actually a fairly big thing, so it's a process. But if you remember this 5-step sequence, the rest of the course is just applying this 5-step sequence for different things. So this is a very important class because it tells you the big picture and gives you a very simple way of remembering the 5 steps. Okay, so what I want you to do is, as usual, take a pen and your notebook, and as soon as for each step I want you to write down the core idea of the step. Okay, so let's go. Okay, before we jump in, I want to remind you about this levels of thinking which has to do with Bloom's taxonomy. Notice that at the bottom end of it is called knowledge, and the kind of things that are required is recall of information, locating, naming, listing, observing, that kind of thing. That's very low level in Bloom's taxonomy. Okay. The next one is translation. Understanding, translating, summarize, demonstrate, discuss. All of that is in the comprehension side. What we are going to do is we are going to have some steps which are out here. There are many of our steps are out here, using and applying knowledge. That's when we start. So 221 is in this range of Bloom's taxonomy. Okay, so this particular class is in this range. Using problem solving methods, manipulating, designing, experimenting, all of that sits here. Then the next one is identifying and analyzing patterns. Pattern recognition is key. So we are going to talk a little bit about this, and we will go further as you go. Synthesis. Now we are talking about creating new ideas, taking pieces together and stringing them together. So looking at all the pieces you got and saying, okay, how do I go from what I have to what I need by stringing pieces together? This is pretty high. And the highest level is evaluation, and that's fairly complicated. You will see that our 5-step process will have all of this: application, analysis, synthesis, evaluation, comprehension, knowledge, all of them. Typically speaking, it will go up this hierarchy. Our last step will involve evaluation. Our last but one step will involve some kinds of synthesis, and then we'll have some analysis and so on. So you will see that we'll have to do everything. Okay, so this Bloom's taxonomy is a very useful way to figure out why certain things are difficult. If they are here, these are called routine or plug and chug problems. If you are somewhere here, if you are here, it starts getting to be a little bit complicated. These are what people think of as trick questions, where I have to put together old concepts and do a new way. And the trick has to do with, can you figure out what to use? Pattern recognition is another trick. Using old concepts to create new ideas is another trick. This is really the open-ended kind of thing, vague questions for which there is no one answer. Okay, so all of these things are involved. Okay, now let's get started. So what do we have to do to analyze a structure? We have to find out what is the demand. Okay, we need to find out how much load is required to be transmitted for a given object to perform properly. So notice, that's the question. Okay, and it could be variety of things. What do we mean by perform properly? It may mean that it has to be rigid, or it has to move, or it has to break at the appropriate time. All of these things are there. Okay, so that's what we mean by we have to find the demand. Then we have to find out the supply, which says, according to the manufacturers or other suppliers, what is the maximum allowable load. So can you see, compare this required, the demand, allowable is the supply, and if it is a non-standard or very critical part, you are not going to take your manufacturer's word for it. You have to test it yourself because it's critical. Okay, but this is what this part is about, supply is about. And in this class we are only going to just look up stuff because this is a little bit higher level, and when you go to a 300 or a sophomore or a junior class and things like that, you will start seeing those things. Okay, right now we are just going to do just this part where we are going to look at the demand, and then supply will be given to us and we can compare and see what happens. Okay, and then the difference between supply and demand is called safety margin. How much do you have left? And that had better be greater than 0. The other way to look at it is supply divided by demand is called safety factor. So when people refer to factor of safety, they are talking about ratio between supply and demand. If they are talking about safety margin, they are talking about supply minus demand. So this is a non-dimensional number, safety factor, safety margin is not. Okay, that's the whole idea. Okay, very good. Before we plunge in, I want to tell you that there are roughly 2 ways in which we deal with structural safety of designs. The first one is called safe life design, which is non-critical parts. The idea is that if you operate it properly, it will last so X number of years. For example, if you have a toothbrush or a fan or something like that, they will tell you safe life. Okay. The other one is that it is what is called a fail-safe design. So this is fail-safe. So some of you may have heard these names. Fail-safe does not mean it won't fail. It means that if it fails, it will fail in a safe manner. It will protect the people. So for example, if you look at a building and there are critical things, you are in there, so there is danger to you when there is a fire or something like that. You cannot make a building completely fireproof. The only way you can make that is not build it. But you can have a fail-safe mechanism which says if there is a fire, then there is a fire drill. So that's a part of the fail-safe system. There are sprinklers. What will happen is the building will fail. I mean, the building will catch fire. But it will catch fire in a safe manner. That is, critical things are moved out, people are moved out, all of these things happen. So this is called fail-safe. Okay. So this is expect the unexpected. And we don't try to eliminate it. We try to say if that happens, how do we protect our critical things? That's how it works. Okay. Those are the 2 designs. So now we come to the question of how do we estimate or calculate requirement or demand or the load. And the idea, you remember HOTS, higher order thinking skill. The higher order thinking skill is the following. We are going to use a combination of the laws of physics and empirical relations. So this is things that we measure in the lab. This is laws of physics. And using those 2 things, we will find the required quantities. Now, a very high level, that's all. Okay. The problem is, these are not simple to do. Using the laws of physics, knowing when to use empirical laws, when to do this is not simple to do. But higher order thinking, that's what you have to do. So, whenever you look at these kinds of problems, you have to say, okay, do I use a law of physics or do I use something empirical? Okay. And then you have to do something about it. Okay. Very good. The target, what I am trying to do is what you have to keep in mind, because you will be in the process of using laws of physics and other things, you will be calculating a lot of other quantities. But you always have to say, okay, is this helping me or hurting me? And that's called diagnostics. We will periodically stop, take a look at it and say, okay, is it helping me or is it hurting me? And the quicker you can do the diagnostics, the better you will be at doing these kinds of things. Okay. And this diagnostics comes with both with knowing the core elements as to when to use what, following a systematic process, and having some experience. Why is this systematic process necessary? Because you know where you are in this scheme. So again, it's that highway business. If you're on the highway, you can easily figure out, get back to your target if you get lost. If you're not on the highway, then it's a whole other thing. Okay, so that's how it works. Okay, very good. So let's see. First step, and I'm going to use Alice in the Wonderland type of things. And those of you who have not read it, it's a very interesting book. It is not just a children's book. It's a lot more. Lewis Carroll was a very, very good mathematician. He wrote about something which is quite philosophically also quite interesting. But Alice in the Wonderland, the idea is Alice goes through the looking glass, that is from the real world into the virtual world. Okay. So the first step is isolate and idealize. That's the step called. What do? We convert the real world object into an interface world. Okay, we create a cartoon world with a simplified representation of the real objects. Okay, this is usually referred to as drawing a free body diagram, but it is actually a little bit more. This is actually called modeling or simplification or idealization. That's why I said isolate and idealize is the core of this. Okay, what is the result of all of this? I'll tell you in a second. It will give you some kind of a free body diagram like what I have shown here. This kind of thing. Okay, it will tell you forces, simplified loads acting on the body at the correct locations and orientations. Can you see there's a coordinate system x1, y1, there's another coordinate system x2, y2, there are forces listed, they're not all put at the same location, they're put at where they are acting. And this is a very important difference between how you learn to do free body diagrams in physics and what we expect in engineering mechanics. Okay, because engineering mechanics is the free body diagram system is actually a lot more critical, so you got to pay a lot of attention. Okay, at this stage there is absolutely no calculation required, but what free body diagram you draw, what idealization you make decides the degree of difficulty of the problem. And so this is very high in Bloom's taxonomy. You have to do a lot of evaluation, synthesis, all kinds of very high level activities. That's why this is one of the hardest things to do, although there is no calculation. So I wanted to understand when it comes to calculation, calculation is the easy. Converting the real world into the interface world is very hard. Okay, we will learn how to do this in a systematic way, but I wanted to understand that's step number 1, isolate and idealize. Step number 2, step number 2 is from pictorial to vectorial. That is, we are now converting all our pictures into vectors, and this uses the laws of physics. And I can tell you that this is an absolutely fixed procedure. This is actually low in the Bloom's taxonomy. This is application of knowledge. This is not very complicated. Okay, but it requires you to be able to do some level of geometry. And if you are not comfortable with geometry, trigonometry and other basic skills which we practiced in Unit 1, this will be very difficult. And the laws of physics, there are actually two things. Sum of all this notation means sum. Right? Sum of all the force vectors on each body must be equal to, sorry, I just jumped back. Sum of all the force vectors in each body must be equal to rate of change of momentum vector. Notice I keep saying vector, vector because this is actually 3 equations. Okay, one in the x, one in the y, one in the z. Sum of all the torque vectors on each body equal to rate of change of angular momentum vector. And in our case, because we are looking at statics, they both have to be 0. This will give you 3 more equations. Right? So you have to do 2 things here. One is convert your all your pictorial stuff into vectorial stuff and then sum them all on each body. So it will tell you that if there are n bodies, you will get 3n equations in 2D. 3n equations in 2D and 6n equations in 3D. Why 3n equations in 2D? It will give you 2 equations here and 1 equation here for 2D. But I want to understand 2D is only a very special case. Real world is 3-dimensional. So, but it will give you 3 times the number of bodies. So I want you to remember this. The outcome of step 2 will be equations. How many equations? 3 times the number of bodies for which you are going to write Newton's laws, or 6 times the number of bodies for which you are going to write Newton's laws. By the way, these laws are not actually called Newton's laws, they are actually called Euler's laws, because Newton didn't talk about torque vectors, he only talked about forces. Okay, but this is the thing, this is the one that generates all the equations. Okay, so next step to being able to do all these equations of motion and things like that is analyze and argument. Well, now is our first very high level decision making point we are at. So what happens is, I drew a free body diagram, that was step 1, which introduced all these forces. I wrote down the equations. Then I look at it and I say, okay, are there enough equations for unknowns? So if there are n bodies, there will be 3n equations. So in 3D, I'll get 6n equations, and in 2D, I'll get 3n equations. By the way, that's Humpty Dumpty. So now we are now at a stage where we are seeing whether we are broken now. You see what I mean? So we are at this is, by the way, in Alice in the Wonderland. So it's a very interesting story of Humpty Dumpty. But you have to see whether your problem is like Humpty Dumpty and it's broken because you don't have enough equations for unknowns. So if there are not enough equations for unknowns, you have to do one of like 2 or 3 different things. First thing is, go back to step 1. That is, isolate and idealize and see if you can reduce the forces or the number of different motions in dynamics. See if you can simplify it in some way. If that doesn't work, then try and see, you have to find additional empirical laws. This is extremely complicated. And it took people a lot of time to figure out that they needed additional empirical laws. And the person who did that is Robert Hooke and Coulomb. So for example, Hooke's law, most of you know, that's an empirical law that relates forces in springs to their stretch. And Coulomb's law has to do with friction. There are other various laws, but these are kind of different kind of laws. I would say working hypothesis or assumptions or something like that. So this is entirely empirical. There are a few critical rules that you have to follow, but mostly they are empirical. If that doesn't work, then you may have to subdivide the body and go back to step 1 and do more equations. So the idea is, as you generate more equations, as you subdivide the body, you generate more forces. But if the number of equations you generate is slightly more than the number of forces you are generating, eventually you may be able to catch up. And by the way, this is how finite element methods do. What they will do is, they will take up a body and divide it into millions of pieces, not 2 or 3. And for each piece, they will write equations of equilibrium or the equivalent of it. And then they will see if they have enough equations for unknowns, add all these empirical things and do it. Okay, so this is very high in Bloom's taxonomy because it needs you to be able to diagnose. It needs you to be able to figure out when you want to do A versus when you want to do B, and there is no magic formula. You just have to look at it and figure it out. So this is quite challenging. Okay, so step 3 is kind of messy. We are now high up in Bloom's taxonomy. You can see step 1 was high, step 2 was low, step 3 is high, step 4 will be low for us. Okay, so somehow you have figured out whether you have enough equations for enough unknowns. Then what? Now we get back. Step 4, you have to compute and visualize. Once we have enough equations for enough unknowns, we have to solve them. And I have drawn on the corner, I have drawn what is called the Cheshire cat. It's because, I mean, computation is like that, is like this Cheshire cat, you know. You try to do it and it will slowly disappear until only its smile remains. I don't know whether you know about this Cheshire cat, it's kind of an interesting thing. It looks kind of easy, but it could be kind of difficult. And it's kind of difficult to grab a hold of it. Okay, this computation requires you to know algebra, calculus, and various ideas in mathematics. Luckily for us, in this course, we will need only limited aspect of algebra. We will need only limited aspects of algebra and a limited aspect of calculus. Okay, so that's all we will need to know. Not a whole lot. So our computation step is actually easy. Visualization is the hard part here. That is, if you compute some number, you have to figure out what does it mean. Where does it? So we are now going to step back. We are now all the way inside Alice in the Wonderland through the looking glass. Now we're going to come out of it. So visualizing is being able to draw graphs, draw pictures, all these things by looking at the computation. Okay. The last step is verify and evaluate. Now this is highest in Bloom's taxonomy. Why is this? Because you have to do some evaluation, judgment. Okay, so first thing you have to do is, after you get a number, you have to ask it, is it reasonable? That is, are the signs right? For example, when we did the chandelier, that hanging chandelier problem, we looked at it and we said, oh, you know what, this is cables, you cannot push on a cable, so better the cable tensions had better all be positive, right? And then, is it roughly correct? So think of it this way: if you get a cable that's pulling a load, and the load is 1,000 pounds, and the cable force is 10 million pounds, you have to ask yourself, am I doing something wrong here, or is this really possible? And does it agree with some simpler calculations? What I mean by that is that, is it reasonably okay? If I increase something, so for example, if I increase the weight, will it go up or down? That's a minimum test you can do. This is called binary. That is, you can say, okay, is my number correct? Will it go up? Will it go down? What will happen? And then you have to then come back to the real world. I have written only one sentence, but this is really complicated. Okay, getting from the number to a decision requires a lot more things. And every time you will have slightly different decisions. All the time you have to ask yourself, am I getting closer to my target? At the end of each step, you have to ask. This is a 6-step process. At the end of each step, you have to ask whether it is closer or not. Okay, now let's see. Isolate and idealize, pictorial to vectorial, analyze and augment, compute and visualize, and verify and evaluate. This is high in Bloom's taxonomy. This is low. Provided you know how to do, this is a fixed procedure. This is high. For us, this is low, because for us, this is high. But what I want you to do is, I want you to memorize this 1, 2, 3, 4, 5-step thing. Memorize the 5 steps. Absolutely, you need to memorize this. Okay. Because we want to be able to do this over and over and over and over again. I will try to follow this exact sequence for every problem, but we are going to do this over and over and over again. Thank you very much.